So we are going to go through the bridge assignment today and then go through some example problems. And then at the end of today, I'm going to talk to you a little bit about how these reactions fit into retrosynthesis. But before we get started, does anybody have any questions about the imine formation or the Wittig reaction? All right, so in general for this quiz, we really only have three main reactions. Some of them go backwards. So you've got like ketone / aldehyde goes to ketal or acetal. And then of course that thing can go backwards. And then you've got that a ketone or aldehyde can turn into an imine, which was that C double bond N, and that reaction can go backwards as well. So both of those are reversible. And then the last one, which is the Wittig reaction, which was the ketone and aldehyde, can turn into a larger alkene, making a bigger chain. So really, it's only kind of those three reactions. They're a little bit, I mean, the ketal and acetal have different names, but it's the same reaction where they just go forward. And then they can go backwards. The same thing with the imine formation and the alkene formation. So these two are the only new ones for today. I hope that what you can see here is that in all of these cases, what you're doing is you're starting with a C double bond O. And in all three of these reactions, you're cutting this bond and getting rid of the oxygen and replacing it with something else. So the ones that we did on last Friday were the product ended up looking like this, where you turn the C double bond O into two ethers. So you replaced a double bond O with two single bond to ethers. Both of the reactions for today replace a double bond O with a double bond to something else, kicking off the oxygen entirely. So for this first one, the imine formation, really all that happens is you turn a double bond O into a double bond N. And that nitrogen brings along with it everything that it had besides its hydrogens. So the hydrogens run away with the oxygen and make water. And we just get a C double bond N, then that would still have those 4 carbons attached. So this is your new chunk, and then we would get water out of that. I think everybody got that right in the bridge assignment. This down here is the backwards reaction. So both of those reactions, the turning it into a ketal, which is what we have down here, or making a ketone or aldehyde into an imine, which is what we've got right here, the C double bond N. Anytime you add water and acid, you do hydrolysis, lysis meaning cutting hydro with water. And we water cut these things back to what they were, which was a C double bond O. So we would take this chunk off and replace it with an O. And we would take these chunks off and replace it with a double bond O. And so this is what your main carbon chain would become. We would also get some of this hydrazine, the NH2, and we would also get some methanol coming off from those. Those are really afterthoughts, more or less. But this would be undoing the imine at this spot and undoing the ketal at this spot and just turning them back into C double bond O's. So this is more or less that imine formation forward and then the imine formation backwards. The next two problems are about the Wittig reaction, which was a little bit more complicated. So the Wittig reaction involves, it kind of seems like it's 3 steps, but it's important kind of keeping track of which ones go together. If you start with an alkyl halide and you add PPH3, triphenylphosphine, and then N-butyllithium as a really strong base, these guys get together and make an ylide. And I don't think that it's completely necessary to be able to walk through every step of the mechanism there, but the idea being that you started off with 4 carbons, and you'll get something similar to what we see up here, where that very first carbon attached to your leaving group, which is currently an electrophile, is going to become a nucleophile. It's going to become that C-. And then your nucleophile plus your electrophile get together. So let's do it up here while we've just got these written out the way that they are. The ylide is your nucleophile. It's the C- right here. And then your electrophile is the carbonyl. And we've seen the electrophile carbonyl pretty consistently for the last month. And those two will get together to make a brand new C double bond C, kicking off the oxygen. So much like we saw up here, we're kicking off the oxygen, replacing it with a double bond N. In the Wittig reaction, you kick off the oxygen and replace it with a double bond C. So the easiest place to mess up here, I think, is to have the wrong number of carbons in the wrong spots. So we should have a 5-carbon chain from our pre-existing ketone. Go ahead and number those the same way. 1, 2, 3, 4, 5. And then you'll have a double bond in the same spot going up this way. And at the end of that double bond will be this carbon, the one that was your nucleophile in your ylid. And so looking at my ylid, I've got 5 carbons here. And you can number them in any way that works for you. I'm going to number them as 6, 7, 8, 9, 10. But this one, number 6, is the nucleophile, which will get together with number 2, which was my electrophile. So this would be my carbon number 6, immediately attached to in the alkene. Then I would have 7, 8, 9. And then number 8 did a little shift off to a number 10. And so this shape right here of 6, 7, 8, 9, and 10 should look a lot like what came from your ylid. And this shape down here, just these 5 carbons in a row, this is what came from your ketone. Any questions on that one? All right, so in order to kind of, this one goes through all of the steps, but once again, we're doing the same thing. Your carbonyl, carbon, which is here, number 2. Down here, it's just gonna be that carbon right there. And the carbon that became your negative charge in your ylid, which was the one right next to the alkyl halide, it's the same carbon next to the functional group. Those are gonna end up making a brand new double bond. So we can kind of count these out. I'll have a 1, 2, 3, 4. And that number 4 would be attached now with a double bond to this one, 5, 6, 7, 8. So you're just gonna have 8 carbons in a row. 1, 2, 3, 4, 5, 6, 7, 8. And to number them all out, we would have, I'll count from this way since it looks more like what I started with. There's my 4 carbons, and then I'll have a double bond after that. And then I would have my carbons 5, 6, 7, and 8. So you can see that the double bond is still coming off of carbon number 5, going towards the new part that I added on, in the same way that carbon number 5 had the double bond to start with. So once again, much like the above reactions, I've kicked off my oxygen, and replaced it with a brand new carbon-carbon double bond here to this isobutyl group, and here to just 4 carbons in a row. So that's the ylid reaction, or sorry, the Wittig reaction. All right, this was maybe a little bit more tricky of a question. Some of you got it right on, which is awesome. I got all kinds of different answers to this question, but let's go back to what is happening in the first place. So let's go back a little bit to Friday. So on Friday, when we talked about the ketone turning into a ketal, if you started off with, say, 2 carbons and an OH in acid, we got rid of that oxygen and replaced it with 2 ethers, and they would be joining on whatever my alcohol had. So O, 2 carbons, O, and 2 carbons. So we would get 2 of these things attached, replacing your C double bond O. If instead of starting with an alcohol with only 1 OH, I started with a diol, the most common of which is ethylene glycol, so it's like this. Then instead of having 2 different alcohols attached, I would just have 1 double alcohol attached. And it would end up making a ring where one side of your OH and the other side of your OH are the 2 oxygens making the ether bond. So it ends up looking like this. So these are the 2 carbons and 2 oxygens that came from here. So basically, if you added a whole bunch of this ethylene glycol, we would do this kind of thing to both your ketone and your aldehyde. But if we only have 1 equivalent, really the question is, which of these carbonyls will react first? And so which of these carbonyls is most reactive? And there is a simple answer to this, but, and I talked about it way back when we went through our ketone and aldehyde naming stuff when I first talked about hydrolysis, but it's been a while. So if you don't remember, it's absolutely fine, but let's work our way toward it. All right. So first question, this is not rhetorical. I would love someone to answer it for me. What is the reactivity of a carbon in a carbonyl? Nucleophile, electrophile, acid-base, leaving group. I just start calling on people if you want to.
Is it it's electrophile?
Yes. Carbonyls have been electrophiles for the last straight month, and they still are electrophiles. Everybody good with that? All right, somebody else, tell me, why is that carbon an electrophile? I'll just start calling. Olivia, why is the carbon in a ketone or aldehyde an electrophile?
Is it because it's attached to the O, which
Yes.
is the leaving group? So it's
Yeah.
because it's attached to the leaving group.
Yeah, so oxygen, I mean, you can think of it as a leaving group. Unlike halogens, it doesn't really leave, but it kind of halfway leaves. But it's definitely more electronegative, so it's definitely pulling electrons away. Everybody good with that? All right, Sydney, what is the difference between this oxygen and this oxygen? It's kind of a trick question.
Is there no difference if it's a
Correct, there is no difference. A C double bond O is a C double bond O for a ketone and an aldehyde. So that doesn't answer our question. All right, but that's what makes both of them electrophiles. Everybody good with that? Yes. Okay, Miguel. If you are a carbon in a carbonyl, what is your major issue? Do you have too many electrons or too few electrons?
The major issue would be too few.
Say that again.
Would it be too few electrons? Would that be the major issue?
Yeah, exactly. So kind of thinking back to last semester when we went through stability of ions, we always based it off of your fundamental issue. Either you have too many electrons, which is usually a negative charge, or you have too few electrons, which is a positive charge. Well, these aren't formally positive charges, but they are electron deprived. So they're partial positive charges. All right. So Caleb, you're in a ketone. How many carbon neighbors do you have?
One.
Try that again. This is you, you're in a ketone. How many carbon neighbors do you have?
3. No, wait, what am I looking at? Jeez.
That's okay. You're this ketone right here. I'm gonna change my color. That green doesn't show very well. Here's my ketone. If you are that ketone carbon, which is electrophilic because it's electron deprived, how many carbon neighbors do you have?
2.
2, right. And what is the effect of a carbon neighbor? This is way back from last semester, but neighbors matter a lot. You don't have enough electrons. Do carbon neighbors share electrons with you or pull electrons away?
Share, right?
Correct. Correct. All right, Kylie. You have a mic?
Yes.
Okay. An aldehyde only has one carbon neighbor. So which of these situations is more stable? A carbon which is already electron deprived but has 2 carbon neighbors to share with it, or a carbon that's electron deprived but only has 1 carbon neighbor to share electrons with it? Which one is more stable?
Wouldn't it be the one with 2 because of the, yeah?
Yes. Yeah. Anytime you don't have enough electrons, more neighbors that share with you make you more stable. So the answer is this one, a ketone, is more stable. So therefore an aldehyde is going to be more reactive. So an aldehyde, so the short answer of all of this is that an aldehyde is always going to be more electrophilic and more reactive than a ketone. So if we only have one equivalent of this thing, well, all these reactions begin because these carbonyls, ketones or aldehydes, are electrophiles. But the one that's more electrophilic is the aldehyde, simply because it only has 1 carbon neighbor. And not just in this case, A ketone is defined as a C double bond O with carbons on both sides, so it always has two carbon neighbors. And an aldehyde is defined as a C double bond O with one hydrogen and either one carbon, or it could actually have hydrogens on both sides. But it's always going to have fewer carbon neighbors, so it's going to be more reactive. So if you want to, just write this down. Aldehydes are more reactive. Oh my gosh. Maybe you can write better than me. Aldehydes are more reactive than ketones. And this will always be true because of what we just went through. These will always have fewer electron donating neighbors. And so therefore they're always going to be more electron deprived than ketone. So they're always going to be more electrophilic, more reactive. So in other words, this whole reaction up here, where we turn a ketone or aldehyde into this 5-membered ring with 2 oxygens, that, like any other reaction, will always happen to an aldehyde before a ketone. And if you only have one equivalent of that ethylene glycol, this would be your product. And so this would be what you would get. So that was tricky. Hopefully took a little bit of working our way through. But if I were to add LAH in only a small quantity, it would attack the aldehyde first. But the whole point of this ethylene glycol was to be a protecting group. So if we protected the aldehyde, which is if we did that first, and then we added LAH, it would only react to the ketone. So we actually kind of get to choose based on using or not using a protecting group, which is part of the reason we have protecting groups. All right, what you'll never see is something that spans 2 carbonyls. I got some pretty interesting answers there, but either they're both going to go on one carbonyl or they're both going to go on the other one. All right, so these are the same types of questions and the same reactions, just thinking about what reagent we would add. And in all of them, you see we start with a C double bond O and start with C double bond O, start with a C double bond O. We replace it with 2 bonds to something else. So in the reaction we did on Friday, which would be this one right here, we've replaced it with 2 ethers. And they both came from an O with a CH3. So to do this, we need an OH with a CH3, or you could have written it this way, just OH with a bond. But you need to have that H plus in there. And that's what's going to put on this OCH3. So just make sure you had the right number of carbons on there. That's the only thing. It does put on 2 of these because you can't make a double bond in an ether. You can't have an oxygen with 3 bonds, at least not neutrally. Over here, what we're doing is we are replacing our double bond O with a nitrogen with 2 carbons. So all we need to add is a nitrogen with 2 carbons. We need to make sure our nitrogen is neutral. So this shouldn't just be N, it should be NH2. And of course, once again, we need acid. All right, this one is a little bit more tricky. This is your carbonyl, and we need to replace that C double bond O with a C double bond C. So we need a 2 carbon chunk. So whatever we're adding has to have 2 carbons in order to make that new bond. So if you scroll up a little bit, or you remember, what reacts with the carbonyl, just like in this one, is the ylide. So we can't start with our carbonyl and add PPH3 and N-butyl lithium because those are the reagents that react with the alkyl halide. So if you started with the alkyl halide, you could add those guys and make your ylide and then react it with the carbonyl. But if you start with the carbonyl, you have to add the ylide. So in this case, what we want is just a 2 carbon ylide. So carbon, carbon with your triphenylphosphine attached. So that would be the correct answer. If you wanted to, you could make that thing in your pot. So basically say, I want a 2 carbon alkyl halide plus PPH3 plus N-butyl lithium. And that would make this thing, but this is what we would need to add to react with the carbon. Any questions on that one? All right, if you had started with the alkyl halide, so if I had said to you, let's start with this molecule, and I'm going to convert it into this molecule, then you know you're making this new alkene. So what we would need to add would be first, you would need to do those 2 steps to turn it into an ylide, so the triphenylphosphine and butyl lithium. And then we would need to add the rest of that thing as step 3 as your carbonyl, your ketone. All right, so that's the bridge. Obviously, this question was not on the bridge, but I wanted to just kind of add some questions that went through everything. If you made mistakes in it, it's absolutely fine. I think the best way to learn these reactions is to make mistakes and try again. But hopefully, as you practice this, you'll see that it's really only 3 reactions, 2 of which can go backwards. So in terms of sheer amount of content, this quiz is one of the smallest amounts of content on one quiz. So I don't pretend that any of these quizzes are easy, but hopefully this will be one of the simpler ones with fewer reactions being covered. All right, let's switch over and just do some practice problems for a little bit. All right, so I'm going to put 3 reactions up here. Work through them all at your own pace, and we will call on some folks to work through them, or at least give us our best answers for them. All right, Mallory, do you have a mic? Maybe, maybe not. All right, Timothy, what'd you get for this first reaction here? What have we done?
This one is you're turning a ketone into a ketal, right?
Right. So what are we getting rid of?
Oh, the oxygen that's double bonded.
Right. And in the product, what will we have attached there instead?
You have 2, I guess it'd be like oxygens with the tert butyl thing.
It's isopropyl.
Isopropyl. Oops.
I know. All right. So yeah, that's right. We would have this chunk right here attached twice. So anytime we add the alcohol, we attach it twice. Kind of a one way to keep track of this is you're kicking off 1 hydrogen, so you're making 1 more bond there. Of course, you're going to get water, but you don't have to write that down. That's kind of just how the oxygen comes up. All right, Olivia, going back, we're going through the order. What's happening over here?
So you're getting rid of the oxygen and
Right.
replacing it with the nitrogen with the not the tert butyl. Is it a tert butyl or the isobutyl?
Isopropyl.
Isopropyl.
Yeah,
But
I know I drew it a little janky, but it's just the 3 carbon split ends, so it's isopropyl. Right, and this would have a double bond.
Yes. Yes.
So when we do it with the nitrogen, we can get a double bond because with the nitrogen, you're kicking off two hydrogens, and the nitrogen can make those two bonds. And you're right, you kicked off that oxygen, so we would also have water here. All right, Sydney, this is the Wittig reaction in the third one. What are we doing overall?
So the negatively charged carbon is attacking the carbonyl carbon.
Mm-hmm. So in my product, what am I getting rid of?
The pH3.
Right, so that'll be gone from this part. What'll be gone from my starting ketone?
The carbonyl
Yep, so once again, the oxygen is gone.
low.
And you replace that double bond O with a double bond to, you were right, this carbon right here, the one that was the nucleophile. So this is your new chunk. So all of these end up looking pretty similar, but when you do the Wittig reaction, you're turning a C double bond O into a C double bond C. And the imine formation, we turn a C double bond O into a C double bond N. And when we add an alcohol, we replace our double bond O with two different single bond O's for ethers. All right, if I were to start with this thing and add acid and water, what do I get, Miguel?
You were to start with the alkane.
Yeah, if I started with just this product right here, which is the ketal, if I added acid and water, what would it turn into? It's actually on this page already.
Oh, right.
It's basically going to go backwards. So it'll take these things off and just restore it to a double bond O. So it just goes back to where we were.
Got it. Sorry.
No, you're good. You want another chance? It's going to be the same answer.
Yeah, sure.
All right. What happens if I start with a C double bond N and add acid and water?
Turn into a C double bond O.
Perfect. Yeah. So we just go back to where we were. All right. I'm not going to call on anyone in specific for this one, but there is a reaction that we did last semester. It's a really cruddy one. If you add acid and water to an alkene, you can add OH and H, Markovnikov, but it's reversible and it's a really messy pile of products. But suffice to say, you can't just undo the Wittig reaction by adding acid and water. So both of these are very simply reversible. This one is not. All right, so the top two reactions go backwards really easily. The Wittig reaction does not, because you made a new carbon-carbon bonds, and carbon-carbon bonds are really stable. All right, questions on any of those? All right, I'm going to give you 3 more, and we will be in good shape. So let's start with this. All right, Kylie, what are we gonna do up here? What is water and acid gonna do to this thing?
Gonna make it into the double bond O.
Right. And so would the double bond O be coming off of the top ring or off of the bottom chain?
The top.
Yeah. So this is the carbon that has the 2 oxygens attached. So that's the carbon that's going to have the double bond O. Perfect. So that would be, this is a weird looking ylid. I know it looks kind of weird because it's 2 rings attached to each other, but you would also get this chunk out, which is 2 oxygens at the end of a 3 carbon chain. So we would get that thing out as well. All right, good call. Caleb, if you start with a double bond O and add hydroxylamine, which is this NH2OH, what are we going to end up with in our product?
You just replace the oxygen with the nitrogen
Yep.
at the double bond.
Yep. And where would the OH go? This part.
Right off the side of the same carbon, correct?
Yep, just right off the nitrogen. So these guys came together and they stay together in your product. And then of course we would kick off water. You don't have to write these things that I've got in parentheses. As always, our main focus is on this, the carbon chain. All right, Mallory, you have a mic yet?
Yes, I got it.
Okay, wonderful. All right, so in this case, I am starting with an alkyl halide. I am adding triphenylphosphine and N-butyl lithium. You know what I'm going to turn this into?
Would it kick off the Cl
Yep.
and add, yeah,
Then what does the N-butyl lithium do? This is what makes one of your carbons reactive.
does it add a double bond?
It doesn't yet. So this is how we make the ylid. So first we add this, and then N-butyl lithium pulls a hydrogen off of that first carbon there. This is how we make that into the negative charge. So this is how we make an ylid. And so we haven't added it to a carbonyl yet, so it hasn't made a double bond yet. But that would be the next step. But this, an alkyl halide plus triphenylphosphine, and then N-butyl lithium as a base is what's going to make this ylid. All right, so this question is not up here, but then I would add that thing, and let's go ahead and use this guy. I took that ylid and added it to a ketone, I would end up making a brand new double bond between my nucleophilic carbon and my electrophilic carbon. So my product of this would be double bond there to a 5-membered ring. So the top would be from my carbonyl, and the bottom of these 4 carbons in a row would be what came from my ylid. And that's where you get that new double bond. All right, questions on any of those? All right, hopefully this feels like it's going to get repetitive as you practice it. So work through those practice problems. There's 2 sets for today. One which is just here starting materials and reagents, what's the product? And the other which is here starting materials and products, what's the reagent? But work through them, pretend they're quizzes, check your answers. I really hope that everyone passes this quiz tomorrow or Wednesday. All right, so lastly, let's look at how this fits into our retrosynthesis. So reminder, retrosynthesis is due this Friday at 1 o'clock. It was posted a couple weeks ago. You can find it in the announcements, or it's on the front page under outcomes 13 through 15, the retrosynthesis ones. It does not cover these reactions right now. It only covered the reactions up and when it was posted. So the last few outcomes, these will be on the next one, which will be posted next week. But this is kind of how you can fit these reactions in moving forward towards next week. So these 3 reactions that we did today, today and last Friday, the first one was how we turn a ketone or an aldehyde into a ketal or an acetal. So these are kind of separate functional groups. They're very similar, but we can turn a ketone into a ketal and an aldehyde into an acetal. And it doesn't change the number of carbons in our chain. So this would all just fit into your functional group interconversion flow chart. So just basically you're adding another functional group and another way to get there. These reactions are reversible. So there's also an arrow that goes back for both of those. Our second reaction was how to make an imine. An imine is a C double bond N to whatever. And we can make an imine from either a ketone or an aldehyde. And that's the only way we make imines. So these will both be kind of like dead ends. So they'll probably be way off to the side for your flow chart, no matter where you put them. We have ketones and aldehydes in there already. Just gives us something new that we can make from ketones and aldehydes. Much like ketals and acetals, imines can go backwards to aldehydes or ketones, depending on where they started. The third reaction, which is the Wittig reaction, should be under your carbon-carbon bond formations because it does make your chain longer. So at this point, I don't remember exactly. I think we have 6 or 7 different carbon-carbon bond formation reactions. So this will just be the next one on your list. Remember what we needed was a carbon nucleophile and a carbon electrophile to make a new bond. And in this case, with the Wittig reaction, our nucleophile was our ylide, so some carbon with a negative charge and triphenylphosphine attached. And our electrophile was a ketone or aldehyde, so a C double bond O. And the product was that we would get a brand new C double bond carbon, with this being my new bond right here. This guy was the electrophile. That carbon up there was the nucleophile from the ylide. And so that's how these 3 reactions will fit into retrosynthesis. 2 of them are just functional group interconversions. Then this one makes your new carbon-carbon bond formation. All right, thanks. That's all I've got for today. Thank you for your patience with me this week. I really hope to be in lab tomorrow. I will plan to be in lab tomorrow. If anything changes, I'll let you know soon, but that's the plan for right now. And if not, I will see you on Friday or next Monday. Thank you all very much.